Hello friends, welcome to our YouTube channel. Now in today's class we will discuss about the resolving power of microscope. Yeah. The resolving power of a microscope is defined as the reciprocal of the distance between two objects which can be just resolved when seen through the microscope. Okay. So here observe this diagram. This diagram will show here the microscope, the lens, it is objective lens. The object is placed at the left hand side of this objective lens and we are getting image on the right hand side. The theta angle, it will shown with the help of this theta here. Okay. Now we will discuss about the when microscope with a pair of non-luminous objects we are using here. Okay. That means the dark objects. In common microscopy, usually self-luminous objects are not observed. Non-luminous objects are illuminated by some external sources. In general, this illumination is not normal but it is oblique. That means if they don't have self-illumination, they will emit others' light. That means they will emit the light that they are reflecting from their surfaces. Okay. Let the wavelength of light in this material be lambda n, and that is lambda by n. Lambda being the wavelength of light in air and n is the refractive index of the medium. In such a setup, the path difference at the first dark ring that we observe here, it is lambda n. And as we know that A is equals to lambda upon 2n sine alpha, equal to lambda divided by 2 into numerical aperture. Okay, where n sine alpha, it is represented as numerical aperture, NA. Okay, so it is replaced here. So the resolving power according to definition, it is 1 upon A. That means R is equals to 1 upon A. That can be represented as 2 into NA divided by lambda, means reciprocal of A. Now suppose the second condition, microscope with self-luminous point objects. So if we are observing from the microscope self-luminous point objects, then here we have to use the Abbey's theory of airy disk. Airy disk we already observed there in relay criterion. Okay, so Abbey's theory of airy disk we are applying here, and Fraunhofer diffraction due to pair of self-luminous point objects. Here the path difference can be given as 1.22 lambda. Thus the requirement of just resolution according to relay, just resolution, how we can get 2a sine alpha is equals to 1.22 lambda n. So when the path difference become this, then we are getting just resolution. Okay, that we already observed that radius of ring can matter here. Thus, for the requirement of just resolution, 2a sine alpha is equals to 1.22 lambda n, and we are getting A is equals to 1.22 lambda n divided by 2 sine alpha. And if we further solve this, for lambda n we can get substitute here lambda by n. So A will become 1.22 lambda divided by 2n sine alpha. So 1.22 divided by 2 will become 0.61. So we are getting here 0.61 lambda divided by n sine alpha, that is nothing but the numerical aperture. So the resolving power, it is nothing but 1 upon A. So finally we are getting numerical aperture divided by 0.61 lambda. So for better resolution, A should be minimum. Means R is equals to 1 upon A. If A will be greater, resolving power will be less. So for better resolution, A value should be minimum. This can be achieved by using an oil filled objective. The objective lens what we are using, here we will use the oil immersed objective lens, which provides higher value of n. Means if refractive index increases, value of A will minimum. Okay, so this is about the microscope and resolving power of the microscope for luminous and non-luminous bodies. Hope you understand this. If you have any doubt, please comment here, like our videos and subscribe our channel. Thank you.